Modern power systems are undergoing a fundamental transformation driven by the rapid integration of inverter-based renewable energy resources, electrification of transportation, and the proliferation of distributed generation. This shift toward inverter-dominated systems has introduced unprecedented operational challenges for transmission and distribution networks, including high ramp rates, reduced system inertia, bidirectional power flow patterns, voltage instability at the distribution level, and frequency volatility at the transmission level. Battery energy storage systems, BESS, have emerged as a critical grid infrastructure asset capable of addressing these multifaceted challenges through fast, dispatchable, and controllable power injection and absorption. Unlike conventional synchronous generation, BESS can react in milliseconds, making it ideally suited for real-time grid balancing and the provision of essential system services. The following analysis examines 6 critical questions that utility engineers, planners, system operators, and regulatory bodies must address to successfully integrate BESS into modern power systems, with particular emphasis on transmission and distribution planning, grid operations, and power system economics. The first fundamental question concerns the role of BESS in addressing distributed energy integration and managing grid load variations in inverter-dominated systems. Contemporary power systems are increasingly characterized by high penetration levels of solar photovoltaic arrays, wind turbines, electric vehicle charging infrastructure, and various forms of distributed generation. These resources introduce significant operational challenges that were not present in traditional synchronous machine-based grids. High ramp rates, rapid changes in power generation over short time periods, can occur when cloud movements affect solar output or when wind conditions change suddenly. This places stress on conventional generation resources that must ramp up or down quickly to maintain system balance. More critically, the reduced system inertia inherent in inverter-based resources means that the grid's ability to resist frequency disturbances is diminished. System inertia, provided traditionally by the rotating mass of synchronous generators, acts as a buffer against frequency changes. When this inertia is reduced, the grid becomes more susceptible to frequency excursions and potential instability. BESS addresses these challenges through multiple technical mechanisms. Time-shifting energy, achieved through peak shaving and valley filling, allows energy to be stored during periods of low demand and discharged during peak demand periods, effectively flattening the load curve and reducing the need for peaking generation capacity. Synthetic inertia and fast frequency response, FFR, capabilities enable BESS to respond to frequency disturbances within milliseconds, providing the grid with the rapid response capabilities needed to maintain frequency stability in low inertia environments. Voltage regulation through reactive power control, QV control, allows BESS to inject or absorb reactive power to maintain voltage levels within acceptable limits, particularly at the distribution level where voltage fluctuations caused by distributed generation can be problematic. Congestion relief without network reinforcement represents another critical BESS function. By storing energy when transmission constraints would otherwise limit power flow and discharging it when constraints are relieved, BESS can defer expensive transmission upgrades and improve overall grid utilization. Finally, islanding and black start support capabilities enable BESS to maintain operation of critical loads during system disturbances and assist in system restoration following blackouts, a capability that becomes increasingly valuable as the grid's resilience requirements become more stringent. The South Australia Hornsdale Power Reserve provides a compelling real-world demonstration of BESS capabilities in addressing these operational challenges. Commissioned in 2017, this 150 megawatts per 193.5 megawatt-hours facility was initially conceived as a response to the South Australian energy crisis of 2016. During which multiple system blackouts highlighted the vulnerability of a grid with high renewable penetration. The Hornsdale facility demonstrated unprecedented performance capabilities, arresting frequency decline within 140 milliseconds of a major disturbance, faster than any conventional generation resource could respond. This rapid response capability directly prevented cascading outages during major transmission faults, demonstrating the critical role that fast-acting storage can play in maintaining system stability. Beyond its technical performance, the facility generated significant economic value, reducing frequency control ancillary services, FCAS, market costs by over 60% in its first year of operation while generating approximately $13 million in revenue. This case study illustrates how properly sized and deployed BESS can simultaneously enhance grid reliability, reduce operational costs, and provide economic returns to investors. The success of Hornsdale has influenced BESS deployment strategies worldwide, demonstrating that storage is not merely a balancing resource but a fundamental grid asset that enables higher renewable penetration while maintaining system reliability. The second critical question addresses optimal site selection and voltage level determination for BESS deployment. BESS siting is not arbitrary. It must be strategically located to solve specific grid problems that align with technical and economic objectives. Engineers must evaluate siting decisions based on the specific grid services that the BESS will provide and the voltage level at which these services can be most effectively delivered. At the transmission level, typically involving voltages between 132 kV and 400 kV, BESS is deployed for system-wide services that affect the bulk power system. These services include frequency regulation, which requires rapid response capabilities to maintain system frequency at 50 or 60 Hz, congestion relief, which involves storing energy during periods of transmission constraint and discharging it when constraints are relaxed, renewable firming, which smooths the variable output of wind and solar resources to make them more dispatchable, and inter-area oscillation damping, which involves injecting or absorbing power to dampen electromechanical oscillations that can threaten system stability. Transmission-level BESS facilities are typically located near renewable pooling stations where multiple renewable resources connect to the grid, at weak interconnections between different transmission regions, or at high-voltage substations with a history of congestion. These locations maximize the BESS's ability to address system-wide challenges and enable the integration of additional renewable capacity without requiring transmission reinforcement. At the distribution level, involving voltages between 11 kV and 33 kV, BESS is deployed for local services that address distribution network challenges. These services include voltage regulation, which maintains voltage levels within acceptable limits for residential and commercial customers, loss reduction, which minimizes energy losses in distribution lines through optimal power flow management, feeder overload mitigation, which prevents distribution feeders from exceeding their thermal limits, and electric vehicle charging support, which manages the impact of growing EV charging loads on distribution infrastructure.